Right. So agenda for this session is we'll try to understand limitations for multi-core CPUs. Then we'll have a brief introduction to this what is a graphics processing unit. We'll see the difference between CPU architecture and GPU architecture. And finally, we'll have a very basic GPU architecture. We'll try to explore that is the first GPU architecture, that is Fermi GPU architecture. Of course, the recent GPU architectures have some modifications, but once you get clear idea about the basic GPU architecture, that is Fermi architecture, then you can easily explore the new architectures. Fine. So these are the some Intel processors where we can have multiple cores. For example, Xeon processors are there with the different series here. We are having 14 cores here, 16 cores, 18 cores, or even 24 cores are there, right? So these are the processors from Intel side, and the different processors are having different multiple cores here with different frequencies, clock frequencies, right? So it is again the trade-off and their marketing strategy, how they are going to manufacture these kind of cores as per the customer requirement, right? But typically we can observe all these cores are having maximum clock frequency around 5 gigahertz, right? Now question is, if we can put multiple cores, so what will be the limit? Why we are only limiting ourselves to maybe only few tens or maybe 100 cores, right? So nowadays you can expect a CPU processor with maybe around, let's say, 100 CPU cores, right? But still we are not even able to go beyond that number, right? We have seen limitations of single core CPU, and then maybe proposed multi-core solution. So that means we'll have multiple cores, but what is the limitation for this multiple cores, right? Is it possible to add infinite number of cores on a processor? No, right? So it is also having some limitation, right? So for example, the limitations like cost. If you compare the price of normal dual core CPU, right, or single core CPU with, let's say, a processor which is promising, let's say, 24 cores. So cost difference will be very huge in case of these kind of two processors, right? So as number of cores increases on your processor chip, then according to that, the cost of that particular processor will also increase, right? So for daily purpose, maybe let's say 4 cores or 8 cores are enough here. But let's say you're working on different problem statements where it requires a huge computing power. In that case, you want to switch from your maybe dual core system to maybe 100 core system. But obviously, if you want to switch from a normal machine to maybe a workstation which is promising 100 plus cores, then of course you have to pay that price, right? So normally, if you try to purchase a device or workstation with 100 plus cores, so cost will be more than 10 lakh rupees, right? So according to that, now you can imagine if we try to increase more and more number of cores, that cost will go, that will be unaffordable, right? So that is one limitation. So that is the reason we are not able to put more and more number of cores on your processor. Next thing is complexity. Obviously, if we are having a single core, it will be having its dedicated cache memory. It will be having its dedicated L1, L2 cache memories. But if you go increase number of cores, then we'll be having different levels of cache memory also, right? Different stages of pipelining that are followed by each core. Then also we have to take care of communication between multiple cores also, right? So this will increase the complexity, overall complexity of your processor. And if complexity increases, it will increase other type of overheads also while performing the computations, right? So complexity is increased. That means if you are having less number of cores, the complexity will be less. More number of cores, the complexity will be increased. And that is the reason, again, it will increase the overhead. So that's why we are not able to go beyond some hundreds of cores on your CPU side, right? Next one is size. Of course, if you are increasing number of cores on your processor, the size of your processor will increase, and hence your entire device size also get increased, And nowadays we want our devices to be as small as possible, right? As lightweight as possible. But if you are putting more and more number of cores, so the processor size will increase as well as the weight of your device also increases, right? So that is the another problem when we go for more number of cores on CPU side. Next, heat and power. We have seen limitation of single core also. If you increase the clock frequency of your single core, then obviously it will start dissipating more amount of heat. And now imagine you are having, let's say, hundreds of cores that are present in a single cabinet on a single board, right? And you can imagine every core is dissipating some amount of heat, and that will increase the overall temperature of your entire device, right? So that's why you need more powerful cooling solution, right? Maybe you are going to put some, those who are familiar with the gaming workstation, they know what is liquid cooling cabinets are there, right? Data centers, who, if you visit all the data centers, they are having their ACs mounted, 3-4 ACs mounted even in a small, you can say, data center room, right? And their temperature will be always less than 16 degrees, right? So the reason is, if you're having more number of cores embedded on a single board, then definitely every core is having its own clock frequency to work on, and every core is going to dissipate some amount of heat, right? So that is the reason, again, you need extra cooling mechanism, and sometimes it may happen that your cooling cost is more than your power that is required to your charge support your computer, right? So obviously cooling mechanism also induce some cost, right? In terms of electricity bill. Likewise, its secondary cost is also increased if you go beyond some number of cores. Next is, if I'm having, let's say now, the limited number of cores. I'll give you a simple example. Let's say a task is performed by a person in, let's say, 100 days, right? So simple solution, if I give is, let's say, the same task is performed by two, let's say, people, then obviously the amount of time will be reduced to half, right? It will be 50 days. If I assign four people to perform the same task, assuming that all the person having same efficiency, then overall time reduced will be 25, right? But let's say the same task, if I assign, let's say, four people, it is going to take 25 days. But if, can you expect the same task will be performed in, let's say, 20 days, if I'm having same number of resources, that is four, the same workers are there, and every worker is having same efficiency, right? So you cannot expect beyond that. Meaning is that if a particular task is done by a single person, it takes 100 days. Two persons, if you apply allocate to the same task, it will take 50 days. But you cannot expect below that, right? So you cannot expect one person is taking 100 days and persons are going to take 10 days. It is not possible. Same thing, if I'm having, let's say, two cores, I can expect performance 2 times better, right? Ideally, if I'm having four cores, I will expect performance is 4 times better, right? So likewise, if I'm having n number of cores, I can expect n times performance, right? I'm telling about ideal expectation, right? Now, let's say if we have limitation of putting multiple computing resources on a processor, then obviously your speed up will be limited, or your performance will be limited to those number of cores only, right? So if I'm having a dual core system, I cannot expect performance 3 times or 4 times. I can expect maximum performance will be 2 times. If I'm having quad core processor, I can expect maximum performance to be 4 times better, but not beyond that. So if I'm having limited number of cores, that indicate your performance will be also limited, or your speed up will be also limited. So these are the limitations for your multi-core CPUs, right? Again, just quick recap. We started with single core system. We tried to improve the efficiency of single core, but we have seen limitations for clock frequency, transistors, etc. Then we proposed multi-core systems, right? Rather than having a single core, we are trying to put multiple cores on the single processor. But again, there are some limitations in this case also, and these are the limitations that are depicted now on this slide. Now question is, this was our second scenario, right? Now next thing is, what is the better solution to have, right? So here the solution is graphics processing unit, right? Again, if you see, the word is processor is again it is a processor, right? So rather than using CPU, we can utilize GPU for that, right? So why we are going, how we can utilize this GPU, what is the architecture, and all those things we'll try to discuss in this session in detail. Now let's try to go back into the history and try to understand when we started working on this GPU. So first term, GPU is coined around 1980s, and the first time NVIDIA in 1999 who marketed the GeForce 256 GPU as the world's first GPU. Right around in 1999, the first GPU was launched by NVIDIA. Now, initially, their intention was to utilize or to design this kind of processor to accelerate the performance of graphics related computations. What type of computations related to graphics? Maybe your games, 3D games are there where extensive graphics is utilized, your 3D environment is there, right? Or maybe some animated animation to prepare some animation, like animated movies are there. So these are the applications where graphics, we refer it as a computer graphics related operation, right? So these kind of applications are having specific computing pattern that is related to your array or matrices. So if you see computer graphics or all these gaming and animation, specifically they work on 3D environment, and that can be represented using different matrices. And the all computations like movements, rotating the environment, scaling the environment, shrinking the environment in 3 dimension. So basically it becomes at the end, it becomes computation of on matrices, right? So these applications are having specific computing pattern, and for these kind of catering these kind of computing pattern, they propose this GPU, that is, and that's why it is named as graphics processing unit. So it used to perform graphics related computations, and that's why it was referred as graphics processing unit. Later on in 2007, NVIDIA launched an architecture that is referred as Compute Unified Device Architecture, or abbreviated as CUDA, right? And which enabled the general purpose computing, right? Not only graphics related, but even normal your sorting algorithms are there. They try to we can try to accelerate using this CUDA programming, right? Sorting, searching, or maybe any general computation in scientific and engineering domain that can be deployed on this GPU. And since then, this GPU is widely referred as General Purpose Graphics Processing Unit, or in short, it is referred as GPGPU, right? So earlier it was intended for only graphics related computations, but nowadays it can be used for any type of computations which demand a huge computing power, right? So this is the graphics processing unit. It is also referred as an accelerator. Why it is referred as an accelerator? So the applications which takes huge time on CPU side, maybe we can deploy it on GPU so that it can execute in parallel, and it will give the results in very less amount of time. That is the what the purpose of your GPU. It is not a standalone device. That means we can have a system without GPU. That means CPU is there, but we cannot have a system with only GPU or without CPU. I repeat my statement. We can have a system without GPU. For example, in my laptop, maybe GPU card is not there. That is okay. I'm having CPU, right? That is possible. But as of now, we cannot have a system with only GPU and there is no CPU, right? So that is the meaning of this standalone device. So GPU is not a standalone device. That means we cannot have a system with only GPU. Can anyone tell me why this statement makes sense? Why we cannot have a system with only GPU?
So GPU is only responsible for graphics, right?
GPU is only responsible for
Graphics things.
graphics. No, but nowadays we can utilize GPU for other purpose also, right? Anyone else? This GPU, your answer is partly correct here. Your GPU can be used for only specific type of computations, right? Which demand a very computationally intensive jobs, right? Kanishk is saying not every process requires intensiveness of the GPU. Exactly, right? Only for particular computations we use GPU because, for example, let's say you want to edit uh, a notepad file or maybe text file. For this kind of application, there is no need of GPU, right? Because GPU is very uh, powerful computing resource, and to perform the normal tasks like editing your MS Word file, or just do some listening to music, right? Or you just want to browse some on internet. So for these applications, you don't need a very huge computing power, right? So even this can be catered by your normal CPU, right? And for that reason, we are using CPU plus GPU architecture, that is called as heterogeneous architecture. Whenever the simple applications are there that can be handled by CPU, which are directly allocate to the CPU. Now, another set of application, let's say most of you are already maybe working on the field like deep learning, where you are want to perform training on different models, right? Let's say your data set itself is in terabytes, right? And your network is having, let's say, millions of parameters to be updated. Now, in this case, you can see a CPU is not going to sufficient for that. If you try to train such kind of a deep learning model on very less powerful CPU, then definitely it will take significant amount of time. Maybe it may take 10 to 20 days also to train a particular model. Now, these kind of application which demand huge computing power, then we can deploy or bypass these computations on the GPU side, right? So the reason why I'm saying GPU is not a standalone device is that not every computation is very intensive and that demand GPU, right? So that's why GPU is not a standalone device. Next is throughput oriented. I'll give you one simple example what do you mean by throughput oriented, and we'll play a small video of a couple of minutes, so that will give you clear idea about what do you mean by throughput oriented device. And finally, it acts as a co-processor, meaning is that main driver of your system still is going to be your CPU, and this GPU acts as only a co-processor, that means supporting to your CPU, because it will handle only computational intensive tasks. Rest of the traditional jobs will be handled by your CPU, and that is going to be the main driver of your system. Fine. Now, these are some application areas where GPUs are extensively used, like gaming and animated movies. Nowadays, those who are familiar with these 3D games, they know what is the importance of the GPU, right? So all this rendering is going to be performed on the GPU side because it requires huge computing power. Then animated movies, like we refer different movies, let's say from Marvel or any other Disney Plus or any other let's say company, right? Pixar or something. So they refer the term CGI, computer graphics very often, right? So when they are referring computer graphics, then that means they're creating a synthetic environment in that scene. And to create that synthetic environment, you need animation or rendering of this environment. And that is the demand of huge computing power that is supported by your GPU. Then other type of applications like in mechanical, that is fluid dynamics is there. That means let's say you want to simulate a turbine based on some fluid flow, then you can perform that using some mathematical background knowledge. You can simulate that and you can display it on the screen how it will work, right? Ideally. Then different domains like drug discovery or molecular modeling also, where you have to perform billions of permutations and combinations to figure out any particular drug will work or not. So for that also, computing power is demanded, then GPUs can be utilized. And the most prominent domain, that is AI, without GPU, we cannot even imagine the AI would have been existed, right? So most of the deep learning training and inference nowadays we perform on this GPUs, right? So these are the some application areas. Now, as I told you, it acts as an accelerator, and CPU is going to main control unit here. So only computationally intensive tasks will be diverted towards GPU, and GPU will perform all these computations in parallel, and it will give result back to the CPU side, right? And again, control will be given to the CPU. So main driver is CPU, GPU is acts as a co-processor or accelerator. Then it is a heterogeneous computing architecture because we are using both CPU plus GPU. These are the two processors in one system, and their architecture is completely different, but we are going to consider it combined as one unit, and that's why we refer it as a heterogeneous computing architecture. Next, it is not an intelligent device. Again, I'm not saying that GPUs are very dumb, but not intelligent device in the sense it takes order from the CPU. So whatever computations GPU is going to perform, as a programmer, we have to give those instructions from CPU side, right? Take this, send data to the GPU, right? Provide some instructions how to execute in parallel, right? All the instructions programmer will write on CPU side, and when you execute, the instruction will be given to the GPU, and GPU will execute all the whatever tasks are there in parallel as instructed only. It is not going to use its own logic. Whatever you provide instruction from CPU, it will follow as exactly, right? So that's why it is not an intelligent device. It just accepts orders from the CPU. Next thing, now point is how many cores we can have on GPU, right? As a simple question, those who are already worked on GPU or maybe having some basic idea about this GPU, at least those who played games on GPU. So definitely you have seen the configuration for the GPU. How many cores that you observed on the GPU, your own GPU? Can anyone tell me? Or maybe what will be your guess? How many cores you can have on GPU? Because on CPU side, we have said we'll be having, let's say, hundreds of cores, right? Somewhere here we said hundreds of cores are there on CPU side, right? But question is, how many cores you can expect from the GPU side? Any guess? Yes, one guess is around 1000 cores, right? Anyone else? Or maybe you can tell the configuration of your GPU, your own GPU. Yes, surprisingly, one okay, again 100 cores. Okay, one of you are having 100 cores. GTX 1650 is having 896 cores, right? So yes, RTX and gaming related GPU is having 3500 cores. Get Sanjeev Kumar is saying 150 cores, right? So typically we can see here in case of CPU, we said that maximum limit is only hundreds, but now you are saying few of you are saying there will be hundreds of cores and thousands of cores are there. RTX is having around 3500 cores are there. V100 is there, that is having 5000 cores, right? Now you can imagine here number of cores that are present on your GPU side compared to CPU side, right? We have seen limitation of CPU that we can have limited number of cores because of all these issues that are associated with that. But on GPU side, we'll be having more number of cores, right? So around latest GPU architecture, if you see, it is having more than 5000 cores, right? It is almost 20 times more than your CPU cores, and that too very advanced CPU, I'm saying, right? Which is going to be very costlier, 100 plus cores on CPU side, right? So these are the limitations of your CPU side, but still we are having GPU which is having thousands of cores, right? We can have over which millions of threads can be launched, right? Threads in the sense we are going to assign different tasks to different threads, right? So let's say you're working on, let's say 100 element array, right? Array which is of size 100. Then let's say I can assign every thread to one element of array, that is 100 threads I can create, and I can perform operation in parallel using these 100 threads. But point here is, the most important is, we can have thousands of cores on the GPU side. Fine. Now it is not a standalone device, that means we cannot replace CPU by GPU, that is for sure, right? For normal tasks CPU is required, only for special tasks we need GPU support. Now let's try to differentiate between CPU and GPU, right? So in case of a single core of CPU, it is very powerful. It is having high clock frequency. It is having a branch prediction logic to avoid that pipelining stalls. It is also having advanced pipelining logic, right? It is having more complex hardware. And it is good for performance. Good for performance means CPU talks about the application to be executed in less amount of time, right? CPU talks about a time as a parameter. A speed of CPU depends on will be measured in terms of time. But in case of GPU, we will be having many cores, like thousands of cores we are having, but every core is not as powerful as CPU core. It is a very lightweight core, right? Which may not have very good power, branch prediction logic, not maybe pipelining support will not be there, right? Even clock frequency of GPU single core will be less than CPU core, right? And that is the reason GPU cores need less power, right? Because CPU is having so many complexities, right? So many advanced parameters are associated with that, and that's why the power consumption of CPU core is high. But GPU cores are lightweight and hence they require less power, right? And GPUs are good for throughput. So there is a difference between latency and throughput. Latency means in terms of time. That means CPU takes care of amount of time required to perform that particular task. But GPU talks in terms of throughput. That means amount of work to be executed per unit time, right? We'll see the difference between CPU, this latency and this throughput with this simple example. Let's say again we are having a task that is digging 400-meter hole here, right? And let's say E stands for efficiency and T stands for time. Now let's say we will say four scenarios here. Let's say first scenario is where efficiency is 2 meter per hour, right? Let's say there is a person whose efficiency is 2 meter per hour. So amount of time required to perform the task of digging 400-meter hole will be 200, right? 200 hours. Now let's say we are having another person with efficiency E equal to 4. So in that case, it will take time equal to 100 hours. Then efficiency E equal to 6, it will take 66 hours, and E equal to 8, then efficiency will be 8, then your total time will be 50 hours, right? So as we increase number of your resources, then amount of time will be reduced. And this kind of thing applicable for your multi-core CPU side, where every core is very powerful, right? You can relate the first example as single core, single core. The second example as dual core. Then maybe here we are having 3 cores, and maybe here 4 cores, right? Likewise, we can relate this CPU or multi-core CPU. So this way, this is how your CPU works, even if we are having multiple cores. But in case of GPU, how it works? We don't have very powerful resources like this. So you can consider the size of this person here and size of person in this GPU, right? So here size is small. That means these are very lightweight resources, but they are in huge in number, right? For example, here we'll be having maybe only 4 such kind of very powerful resources. That means we'll be having 4 CPU cores, but every core is very powerful. In case of GPU, we'll be having here 64 cores, but every core is not will be a lightweight core, right? So if you see efficiency of a single person is here is 2 meter per hour, but efficiency of single person in this case is 0.25 meter per hour, right? So now, but here we are having 64 such number of resources. So overall efficiency is going to be 64 by 0.25. So that will be your overall efficiency of these resources. And the overall time required will be 25 hours now. So here we had very powerful 4 resources and overall time was 50, right? But now here we are having very lightweight resources, but they are huge in number, and that's why overall efficiency is high and total time will be 25 hours here. So on this idea, your GPU works, right? We don't require very powerful CPU cores, right? Rather than we'll be having very lightweight cores where every core is having less efficiency, but they are in huge number. That is the whole idea behind the GPU, and that's why it is referred as throughput oriented GPU or throughput oriented device. Right, so this is the overall idea between difference between your CPU and GPU, right? So give it a very short idea here or recap what we have seen in case of CPU versus GPU. So number of cores in case of CPU are limited till few hundred, but in case of GPU it is in thousands. In case of CPU it is more intelligent, GPU is less. We can have standalone CPU, we cannot have standalone GPU. CPU is latency oriented, GPU is throughput oriented. The clock rates of CPUs are very high, but nowadays you can say CPU you can expect till 4 gigahertz, and GPU is also in few gigahertz you can expect, right? The efficiency of CPU is more in case of sequential execution. GPU is more efficient in case of parallel. Again, we can also have parallel computing on CPU side if you are having hundreds of CPU cores. That is also true. Power consumption for CPU is more and power consumption of GPU cores is less. CPU cores are very powerful compared to GPU cores, right? CPUs are used for general purpose and GPUs for special purpose. Its role is CPU is main driver of your system, that is a processor, and GPU is a co-processor, right? On your motherboard, you'll be having some slots to plug these GPU cards. So these GPUs are plug and play device, right? That means you can have a board where there will be a few slots to plug your GPU cards, or maybe you can remove older GPU card and you can plug a new GPU card over there, right? So it is a plug and play device, right? So in this is another difference here according to the architecture here, CPU versus GPU. So on CPU, most of the area is dedicated for your cache and control logic, right? According to this, most of the space is utilized to have a cache memory and this control logic. Whereas in case of GPU, most of the space will be utilized for your cores or computing resources, right? More areas dedicated for your cores, right? One important thing is that here in case of CPU, it is having its own dedicated memory that we refer it as a RAM, right? Because CPU is a processor. Whenever you want to execute any application, first of all, its data will be fetched into the RAM, right? So that's why for CPU, we are having its own dedicated RAM. Similarly, if you want to perform any computation on GPU, its data needs to be stored into its own memory, and that is also referred as RAM for the GPU, or sometimes it is referred as VRAM or video RAM, right? So in case of GPU, also it is a processor. So whenever it want to execute something, right? So the data must be residing its own memory. So for CPU is also having its own dedicated RAM, and for GPU is also having its own dedicated RAM here. Fine. So this is what your difference between CPU and GPU. Now, this is a typical hardware architecture of the GPU. That is here. Let me just zoom in a little bit if possible. Okay. So you can see this is the GPU architecture inside which we are having some blocks here. So here 4 blocks are there, inside which every block again there are 4 blocks are there, right? So I'm not sure whether it is visible for you guys. From your side, you can zoom in, right? You just have to scroll on your screen so that it will zoom in. You'll see here is something is called as stream SM. That is called as streaming multiprocessor. So in this part, we are having 4 streaming multiprocessors, right? Likewise, we are having total 16 number of streaming multiprocessors here, right? So total we can see 16 blocks are there, and that one block is referred as a streaming multiprocessor, right? So in this architecture, it is mentioned 16 number of streaming multiprocessor. Now let's try to zoom in one streaming multiprocessor here. So you can see one streaming multiprocessor looks like this. Now in one streaming multiprocessor, here we are having 32 plus 32, 64 cores, right? A single, this rectangle, green rectangle indicates one GPU core. And how many cores are there in one streaming multiprocessor here? 64, right? And now we are having 16 number of streaming multiprocessor, and every streaming multiprocessor is having 64 number of cores. So how many in total number of cores in that GPU? Can you answer? 16 multiprocessors, and every multiprocessor is having 64 number of cores. So what will be the total number of cores here? 16 into 64, right? So these many cores are present in your GPU with respect to this architecture. Fine. Now again, this is very basic GPU architecture, but in maybe recent GPUs, you may find out that in one streaming multiprocessor, maybe there will be 128 cores or 256 cores, and we'll be having multiple, let's say, such kind of streaming multiprocessor, maybe 16 or 32, likewise, right? So this is how we calculate total number of cores that are present on your GPU. Fine. If you zoom in a little bit more, a single CUDA core, so you'll find out there will be floating point unit to perform computation, integer unit to perform computation. Likewise, you can go in detail. But as of now, it is not required to go in much detail, right, inside the core. Now, for every streaming multiprocessor, there is a cache memory dedicated. And that is we are having here, right? Or you can see here, for every streaming multiprocessor, this blue color indicate the cache memory, or it is also referred as shared memory, right? Just like your CPU, it is having its own cache memory. For every streaming multiprocessor, we will be having its own cache memory, or we refer it as a shared memory. And purpose of this cache or shared memory is same again. We are going to put very frequently used data into that shared memory or cache memory, so that the future access will be served immediately without making any memory transaction, right? So that is the overall GPU architecture or basic GPU architecture, right? Now I will play a very short video that will give you brief idea about how CPU is different from GPU. Okay, just give me a second so that I can play that video. You may not get audio. I will share that link with you also, so that if let's say it is buffering in presentation, so that you can open in your local system also. I just dropped that link in MS Team chat. You can open that link, or maybe you can watch with me also. Okay, so I'll play this video.
CPU might do.
Sorry, it is echoing. So you just observe the video, right? No need to audio also. I'll explain that. Those who want to watch video in their local system, they can watch. So basically, they are trying to demonstrate how GPU works and how CPU works using a normal, you can say, your painting application, right? So first of all, you see that entire video, then I'll explain what is going on. So here they are demonstrating how CPU works, right? And now they have another machine that will demonstrate how GPU works.
Yeah, அவனது ரூம்ல தானே இருக்கும். இங்க இல்லையடா.
So you can observe this machine is quite big compared to your previous machine, but ultimately they are trying to paint something, right? Now you have seen how they try to paint using a small gun that we can relate to CPU. Now they are demonstrating how GPU works using this machine. Right? So this device painted Mona Lisa. Right? Now I'll just quick go back and I will again play some portion of this video. Here they try to demonstrate how CPU works step by step, right, in sequential manner. Now they started this application and you can see this gun is throwing one paintball at a time, right? That is sequential. That means first of all it is throwing paintball at this location, next at this location, followed by next, and so on. It will paint. Now while painting is happening, meanwhile the person is trying to increase the speed of that device, right? So can you relate to your CPU parameter? Which CPU parameter is more appropriate here to increase the speed? Anyone? Speed, right? So we are trying to increase the speed of your CPU. How you can increase the speed of your CPU? By increasing which particular parameter? Yes, clock frequency or gigahertz, right? Same thing is happening with this person also, who is trying to increase the speed of that device. That means it is increasing the clock frequency, means it is trying to paint or throw more number of balls, paint balls in 1 second, right? So the person increases and you can see the speed is increased and it will start painting at very faster rate. So this is how sequential CPU works, right? And the next, here we are having this device, right, where you can see it is having multiple such kind of paint machines are there, right? So nozzles are multiple here, and from every pipe they can throw paintball at the same time, right? And that is the reason you can see in one shot itself it is printing or it is throwing all the paintballs in all the location in that image, right? And you can see in the one shot itself it is printing all the or throwing all the paintballs, right? So this is how your GPU works. So we'll be having thousands of cores and every core can perform desired task independently and every core can perform at the same time, right? If you follow the sequential one, first of all it will paint the first you can say here, then gradually it will try to print one row, the next row, the next row, as like sequential application. But GPU will be having thousands of cores that can be performing operations using multiple threads at the same time. Fine. So with this, we can conclude this presentation also, where we tried to understand the difference between CPU and GPU. Now tell me, I'll wait for a couple of minutes where you can ask questions if you have any. Yes, any doubt? If you have no doubt, those who have closed those cloud instance, you are supposed to restart, right? Because it will take 5 to 10 minutes. So make sure to restart this instance so that you will get access. In my case, the time is elapsed, so that's why that instance is closed. Now again, I have to relaunch that instance. So for that, I have to restart it. So restart those who are already closed, or those whose time is remain very less, 4 to 5 minutes or 5 to 10 minutes. They can also stop the task and again restart, so that you'll get 3 hours of time. Okay, meanwhile, if you have any question, you can ask. So all these courses are having multiple chapters, right? I will try to complete most of them, but there are some assignments are there, or maybe some advanced bonus concepts are there in every chapter that you have to explore after the training, or maybe after 5 p.m. right, at night, or likewise, right? So important topics I'll cover, because all these courses are self-paced. You can read the text from all these notebooks, right? You can perform, all the instructions are already provided in that. You just have to practice it, and accordingly you have to solve all the assignments, right? Any doubt till this point? I hope all of you received the presentation files. The evaluation Excel sheet is also there. So you refer that, right? And accordingly, you have to work on all the assignments, certifications, and the interview rounds. Okay. So in my case, it is showing the launch button now. So I can launch. So once you click on launch, it will open a Jupyter notebook, right? So where this is the environment where you can see the instructions, the text in the text format also. Plus, you can practice your coding assignments here only, and you'll be able to see the presentations as well, right? So here, those who are not familiar with this Jupyter environment, so there are some buttons that you are going to use frequently. For example, let's say I want to execute this command. So it is referred as a cell, and you can click in this cell and you can click on this run button, or you can simply press Control plus Enter, right? So once you click on run, it will start executing, and you'll see here for some time the star will appear here, asterisk, right? So that indicates you are currently this cell is executing, right? Either you use this run button, or you can use Control plus Enter to execute, right? Next thing is, let's say you start working on it, and let's say you want to refresh everything, then you can go to this kernel and you can execute, restart, and clear output. That means your all the output from all these cells will be removed, right? Cleared from the main memory, and completely a fresh notebook will be provided, right? But carefully, because once you go on modifying and if you refresh, then all your progress will be lost, right? Whatever you have executed in the previous cells. Don't again try to jump on directly executing any other cell directly, because step by step you have to follow. This is a Jupyter notebook, so it is important to execute the first command, then you can go for the next, right? Because it is interpreter kind of thing. Next thing is, let's say you want to interrupt the cell. That means sometimes it may happen that you're not able to execute any of these, maybe due to some technical glitches there. Then you can stop it completely or interrupt the cell, right, while executing, or maybe directly restart, right? Now you will be able to access this Jupyter notebook for 3 hours only, right? After that, again, if you try to execute any command, it will not allow you, because your cloud instances will be closed, and again you have to restart it, then only you'll be able to execute. Whenever you are going to restart it, again launch new notebook. Don't use the old notebook. Fine. Okay. Now this is your first chapter in the certification of CUDA, fundamentals of CUDA programming using C++, right? So here, what is expected from your side? You just must be familiar with simply writing different for loops in C programming. You must be aware about how to write function, right? Then if else statements in the C, and you must be familiar with memory allocation, deallocation, or working on arrays. That is what required, right? No previous knowledge of CUDA is required here to work on this assignment. And you will see throughout this Jupyter notebook, all the instructions are mentioned, what you are supposed to do, right? The strategy that we are going to follow is, first of all, I will give you few minutes to read the paragraphs or read the instruction that are mentioned here. Then I will explain what are the, I will walk you through all the presentations, what are there, right? Then you'll practice in this Jupyter notebook only. So they are providing some instruction how to practice, and some exercise problems are given, right? For few exercise problems, there will be solution. If you click on solution, you will get immediate solution. But for few exercise problem, there won't be any solution, right? Like for this particular certification, at the end of course, there are some problem statements. One problem statement will be given to you, for which solution is not mentioned anywhere in this particular course. Based on whatever things we discussed throughout this course, you are supposed to apply that logic to solve that programming assignment. And once you solve that assignment, automatically it will be graded, right? Automatically it will be evaluated, right? If your answer is correct, then you will get full marks, and immediately you will get certificate for that, right? Immediately you will get digital certificate in the progress bar. So you can see in my progress bar, if I go over there, so it will say this marks. So I got 100 out of 100 marks here. So that's why it is indicating these two histograms 100 out of 100, right? And finally, you will get certification in your that progress bar, right? Now, these are the objectives from this chapter. We'll first of all try to write, compile C++ program, both called CPU function as well as GPU function, right? We'll try to understand thread hierarchy. We'll try to convert a serial loops into parallel loops. We'll understand how to allocate memory on CPU side and GPU side, right? Error handling technique is also mentioned, and finally accelerate some applications on the GPU side, right? So these are the objectives that we are going to follow in this chapter. Now, here, let's say you want to find out on which GPU you are working. So there is a command NVIDIA underscore hyphen SMI. But before that, you have to use this exclamatory mark, so that that means that this particular command is operating system related command. That means you are giving some command to operating system. And if I execute this cell now, right, I'll press Control Enter, or simply I press Run here. So if I press Control Enter, so it will show the details of GPU. In this case, I can see here there is only one GPU is allocated for me, and that's its name is Tesla T4, right? So this is the GPU that is allocated to me, and here the configuration is mentioned, that is 50 100 MB, that means 15 GB of memory is there for that GPU, right? And out of which 0 MB is utilized because we have not executed any program on the GPU. So that's why it is showing 0 MB. Then here we'll be having utilization of GPU. That means out of all the cores, how many cores are being utilized, right? We have not executed any program on the GPU, so that's why it is showing 0% utilization. Fine. So this will give you the details about this GPU, because you don't need any GPU in your local system. You don't have to install any package for CUDA programming, right? Everything is pre-installed. You just have to work on the assignments. Fine. So this is the GPU that is allocated to you. Now next section is where some presentation is there. Again, here also you just have to execute this using Control Enter, and your presentation will pop out, right? So you can start presentation here. Okay. So either you can parallelly open, or maybe you can refer to the presentation that is shared on the screen. So here, as I told you, whenever you write any CPU application, right? First of all, what you do, you will allocate memory, right? Declare variables. For example, let's say you are working on C++ program. Let's say you want to perform matrix multiplication. Then what you do, first of all, you declare variables for matrices, let's say A, B, C. Then you will allocate memory to those variables, right? Based on whatever size of matrices. Then you will initialize those matrices. Then you will compute all this matrix multiplication computation, and finally you store the data into the another matrix, right? So here in this presentation, there's a timeline is provided here, right? On x-axis we are having time. On y-axis there are two components. One is data and CPU, right? So CPU indicates what are the computations you are performing. Data indicates the amount of data that is stored in your RAM, right? Now we are just looking for your normal CPU based application. Here, first of all, when you perform initialize, then data will be allocated to that particular variables, right? When you perform work, that means you are performing some operation on that data, and finally you are going to verify that work whether the results are correct or not, right? Now, in case of GPU, when we are having GPU also in your system, then you are having two processors. So I am mentioning here CPU plus GPU here, right? So in this section, we'll mention the CPU related functions, and in this section, we refer the GPU related functions, right? Then in data also, as I told you, CPU is having its own memory and GPU is having its own memory, right? Because both are the processors. So if they want to perform any computation, they need data in their local memory. And for CPU, we are having local memory that is referred as RAM. And in case of GPU also, it is having local memory that is referred as VRAM, or again, you can refer it as a RAM also, right? Now, initially, let's say you initialize data on the CPU side. That means data is present on the CPU side now. Now, let's say you want to perform that work on GPU side. Now, what will happen? Of course, GPU, you want to perform that computation on GPU side. So this data that is present in CPU RAM must be transferred to the GPU first, right? Because you want to perform that computation on the GPU side in parallel. So obviously, the data must reside into the GPU memory. A simple logic is that whichever processor you use to perform that computation, the data must reside into that particular processor's main memory, right? You are performing initialize operation initially, so data was present on the CPU side, right? Now you are performing some operation on that data on GPU side, so the data is transferred from CPU to GPU, right? Then let's say while you are performing any operation on the GPU side, meanwhile you can utilize CPU to perform other work also, because once you provide instruction to the GPU to perform some operation, during that time CPU is sitting idle. Either you can allocate any computation to the CPU, or you can ask CPU to wait for some time till GPU finishes its job, right? Now after some time it will be synchronized. That means CPU will complete its execution and GPU will also complete its execution, right? And then again you are going to verify whether results are correct or not on CPU side. Now this verify work is executed on CPU side, so data will be again fetched into the CPU side here. Now data is present on the CPU side, right? And likewise, we can say this is how your computation happens on CPU and GPU side. So key takeaway from this presentation is, whenever you want to perform any computation on CPU side, the data required to that computation must reside on the CPU's main memory, that is your RAM. If you want to perform any operation in parallel on GPU side, right, the required data must be transferred from CPU memory to the GPU memory, so that data will be available on GPU memory, and on GPU we can execute the operations in parallel by referring that data. Fine. Any doubt till this point? Simple 10 slides presentation is there. If you have any doubt, you can ask at any time, right? Now, let's try to write a function that will be executed on GPU. If you recall, I told you that here you don't have to learn a completely new programming language syntax, right? We'll be using your C programming language, and in C programming language only we are going to modify a function so that it will be executed on the GPU side, right? So here now we are having main function. Inside there are two functions. One is called as CPU function, other is called as GPU function. As of now, don't worry why we are having this crazy syntax here, right? Some angular brackets are there. Okay, I'll explain step by step each and every parameter why we are using this, right? But as of now, let's try to understand what is this template, right? We are having main function. Inside that we are calling a function that is called as CPU function, that is normal C function. Then we are having another function that is called a GPU function, right? And followed by that, we are using this CUDA device synchronization, right? Then let's see, according to the definition, how CPU function and GPU function is different. So this is your CPU function. It is typical C function, and this is GPU function, right? Only new modification here is we are having this global keyword, right? It is underscore underscore global underscore underscore, right? So this is prefixed before your function definition, that is void GPU function. If you remove this global keyword, then it indicates it is a CPU function, right? So once you explain, write this prefix as a underscore underscore global underscore underscore, that indicates this function is supposed to be executed on GPU, right? So compiler will automatically understand that using this keyword, this function is supposed to be executed on GPU. That means you are annotating a function with this keyword so that compiler will understand this function is to be executed on the GPU side. But first point, why we are using this global keyword? Now, next thing is, while function calling, we are using, this is called as thread configuration in case of this GPU function, right? So obviously, as I told you, let's say you want to exploit, let's say, multiple cores on GPU. So we'll create multiple threads, right? So multiple threads means we'll be having multiple computing resources here, right? And every thread is going to perform a specific task, right? So before we deep dive into this thread and block configuration, as of now, you read these statements, and here in the next exercise, there is a hello GPU function is there, right? If you click on this function, hello GPU.cu, right? So it will open a new editor, right? And where the complete program is mentioned and all the instructions are mentioned. You referred the previous GPU function here, CPU function and GPU function. Now it is asked that you are supposed to modify this particular code so that hello GPU function will be executed on GPU side. Okay, so for that reason, take 2-3 minutes first of all read all these statements, right? What is purpose of them, and then you go and try to modify this hello gpu.cu, right? I'll give you 3 to 4 minutes to complete this task. Read first this complete text and then try to modify this hello gpu. If you stuck at any point, you can click on solution here, right? It will give you solution, but better first of all read all these statements and then you try to modify this hello gpu.cu. Meanwhile, if you have any query, you can ask. Okay, how many of you are able to modify that function? Can you raise your hands? Okay, I'll just guide you what to do in this particular function. So here again, main function is given and we are having hello CPU function and hello GPU function. If you see those definitions, just like your normal C function, right? So both will be executed on CPU side only. Now what is asked us, we have to refactor the hello GPU definition to be kernel that can be launched on GPU, right? And update its message to read hello from GPU, right? That is what required. Now you tell me what is the first step you will perform if you want to convert this hello GPU so that it will be executed on GPU. Anyone? I want to tell compiler that this function is to be executed on GPU. What will be your first step?
Underscore global before void.
Global keyword that we have to use, right? So I will use here underscore underscore global underscore underscore and space. Now this will ensure that this hello GPU will get executed on GPU side, right? But problem is that here this is function definition we modified, but not yet function call, right? In function call, we have to provide thread number of threads you want to launch, but as of now, because you don't know what is the concept of thread and how they are organized, I'll just copy paste what is mentioned in that previous description, right? Now this is how we modified this hello GPU function call so that it will be executed on GPU, right? Now you can go back here in the Jupyter notebook and you try to execute using this command, right? Command is already mentioned. So here we'll be using NVCC, NVIDIA CUDA compiler, right? NVCC. Then here some flags are mentioned according to the architecture. Even if you skip that, that is also fine. Next thing is here we are providing path of that particular file where it is stored, right? We are assigning the name to the output file, that hello GPU, and finally we are executing using this run command, right? So if I run this now, we'll see the output of whatever we have modified here, right? So I will execute, save it and execute, right? We are getting hello from CPU, right? The function is getting executed hello from CPU, but we are not getting message hello from GPU. A simple hello world program is there. Now we are not getting message from GPU. So if I execute one more time, you'll see we are getting message from only CPU side. Can anyone tell me why this is happening? Though we have written, modified both the functions, but still we are getting only hello from GPU, that CPU. That means only this function is getting executed, not GPU one. Yes, right. We have to synchronize. Now what will happen if you see here at this point, CPU now CPU start executing this main function. CPU will call this hello CPU, because normally whenever you write a C program, the complete instructions will be executed by the CPU, right? And instruction that needs to be executed on GPU, that we have to specify explicitly, right? So we said that hello GPU function to be executed on GPU. Now once CPU calls this function, CPU is not going to wait till this function completes its execution on GPU side, right? CPU will immediately go to the next statement to execute. And what is the next statement to execute? These are the comments, and after that we are having closing bracket here and the closing bracket of main function, right? So CPU call this function hello GPU and immediately it will terminate the program itself, right? So before GPU prints that statement hello from GPU, the complete program is terminated by the CPU side. So we'll miss that particular message from hello from GPU. Now we'll try to synchronize using this CUDA device synchronize. I'll copy paste after this hello GPU, right? I'll save it, and again I will come back and execute this program, and you'll see now the both hello from CPU and hello from GPU is executed. Now why this is happening? When you mention explicitly here CUDA device synchronize, you are telling CPU explicitly that don't rush to go and execute next statement, wait till GPU completes its execution, or whatever function previously executed on GPU, you have to wait till that point. Meaning is that when CPU calls this function, right, immediately it will encounter this CUDA device synchronize that tells CPU that don't go further, wait till GPU completes its execution, right? And once the GPU completes its execution, then you are allowed to go further and execute next statement. So after this CUDA device synchronization, next statement is curly bracket, end of curly bracket of main function. Now your program will be terminated after printing the hello GPU from the GPU side, right? So this is what your first simple assignment, to write a simple hello world program on the GPU side. Fine. Now you read all these statements till this step, right? Till this exercise, right? We will have a short break of here for 10 minutes, right? And after 10 minutes, we will again continue with the next topic, that is compiling and running accelerated CUDA code, right? We'll go into the details of all those things. What is compiler, what is architecture, how we are creating an output file, etc. Then we will see a short presentation of thread hierarchy. Then we'll try to modify different coding exercises. Fine. So meanwhile, we'll have here a 10 minutes break here. You go through all these environment, because this kind of environment will be frequently using for next 3 to 4 days, right? So make sure to go get familiar with this environment, try to execute all these codes, try to modify, edit also, and read all the statements very carefully, because if you read all the statements carefully and if you follow all the assignments carefully, definitely within maybe 10 to 20 minutes itself, at the end of this course, you'll get certification, right? The programming assignment for this course or certification is not very difficult, right? You just have to pay attention for the whatever topics you are learning, and based on that only you'll get the assignments problem statements. Fine. So now it is 2:35. We'll join back at 2:45. Okay, we'll have 10 minutes break here. Meanwhile, if you have any questions, you can drop on MS Team chat or maybe on WhatsApp.